let's wait a few minutes before we start because we just wait everyone to come in. Let's say 1 or 2 more minutes before we start. Maybe we should start. I guess it's 5 minutes past. So what's the goal today? We will be working on the linear regression. We cover more than half of it, and then we will cover the rest next class, and then we've done all the course material. And because next Thursday we can't have class because of the there's no class on that day because of the school holiday, so we cannot talk about that. Then the quiz will be on the first and the Tuesday afterward. Okay, so that would be the plan. So any question about the material we have covered so far? If you have any, any question? If no, then we are going to start talking about linear regression. Okay. So just to review what, just to preview or review what we just briefly covered last time is linear regression. And linear regression is the technique that you try to understand the relation between two variables, say x and y. And here x and y are numeric variable, usually it's a continuous variable in our mind. Okay, so usually it's something like income and years of education. Okay, so continuous or discrete also fine, but just we can consider education. Year education is still a continuous. Say something about advertising expenditure versus sales. Okay, you want to study how they are related, right? You tend to see, importantly, you whether want to study whether sales are related to advertising, right? And then you can calculate how effective of the advertising, right? Is whether worth spend the dollar to do the advertising, right? And maybe you can estimate how the sales is affected by, say, advertising in newspaper, advertising in TV, and then you will try to see where would you, if you have additional money to spend with a newspaper or radio or TV, right? Or internet, okay? So here you can see we are studying the relationship with two variables. Okay, can you see the slides? I forgot to ask. Yeah, so you can see the single observation here is in pairs because we're going to study in pairs. So 3, 4 is different. 4, 3 is different from 4 and 3, right? They're different, okay? Because the order, the matter, right? Because they represent a variable like this way, right? Because the data, what you have in Excel, you will have spreadsheet X and Y, 1, 2, 3, 3, 4, 5, and this usually data you see in the column form or in the row form, but that's pretty easy. It's a column form. Here, linear regression, here is linear. You try a line, okay, to best fit all the points, okay? And here the y is connected x for a linear version, right? This is the y-intercept, right? This is the slope, right? If you remember your analytic geometry or coordination geometry, this is the slope-intercept form, right? Is y equal to c plus mx, right? Exactly this form. C is intercept, m is the slope. And so this is, we try to find a line to explain this, right? Here I just use one variable. If you use another variable, then it's longer a line. It will be plane, right? Because you want to explain this by plane, a three-dimensional graph. If you have more and more, then you will not be visual in a three-dimensional world. We need 4-dimension, 5-dimension, which is not easy to draw, or usually you can't draw it. But there's no need to stop from there. You can go any dimension. And here, simple, as I said, we just use one, right? And linear, we focus on they are related linearly. You draw a line. You don't fit a curve, right? And what's nonlinear? Say, suppose if you do this, then it's nonlinear, right? So basically, you are something like, if you have data like this, okay, then probably you want to fit a nonlinear curve in this way, right? So, but here we focus on linear one, okay? So, something like this, then is nonlinear, okay? But do note that if it's not that restrictive, say suppose you just, if this is something you want to run a regression on, you can still run the regression by saying that creating variable x, okay, x squared become x, okay? So you just square the data and it constant itself, then it's still a linear regression. So it's linear just in terms of the variable you propose, but you can transform the x variable. You can take the log, right? Sometimes you will see people will do this, okay? This is, you see this a lot of regression like this, okay? Or another regression would be like this, that is something you would sometimes also see, okay? Both take log, okay? Log will be the growth rate. For those who do finance, then probably you will notice that it is common, you take the price, you take the log, then will be the, it will be approximate return. And if you run the regression like this, then this is sometimes you do the CAPM model, then you put the market return at the Y, market price, market index, and this is the index, and they give you the beta. But anyway, that's not the concern here. If you go to study asset pricing, they will tell you more. But for the moment, and then we don't need to concern ourselves on this. So any question? If no, no question, then we are going to do the second part. No question, right? So let's, so I add one slide here just to say study advertising, sales, education, income, drug dose, and recovery time. There are many things I study, but anyway. So this is a simple linear regression. It means, okay, so this is a variable x and y, and then how you try to find a line, okay, and this is a point, this data you want to see, you want to find a line that best fit, okay, that will be to find a line that fitting it very well. But what does it mean very well? Is it a good line? Probably not, right? Because it's too far away. Is it a good line? Probably it's not. How do you determine whether a line is good or bad? Is we define to be the vertical distance, to be the thing we want to minimize. So this is, say, I want to minimize this distance, okay? Is how, given the same x, okay? There's a data here, there's a line here, I want to minimize this distance, okay? And minimize distance, how you add up the distance, we do it in the way that we do the variance. We take a difference between the vertical distance, okay, and square it and add and all up, okay? So each point to this is distance, you square it and add all up. So add up all the distance. Then you want to find a line that would minimize this sum of square distance. Okay, so that's definition. So that is what it means. I add this slide to recap, but there's no different from what you have right in your one. Oh, I should be. So it should be yi minus alpha minus beta xi. Okay, so so this is the data here. Okay, and this is the line we try to say the model, right? Alpha plus beta xi is the yi hat. Y hat is the coming from the model. So the vertical distance is yi minus y hat. That is yi minus alpha minus beta I. Okay, so the sum of vertical square difference, right, will be this. Take the square and adding up all the data points. Okay, and what we care is we try to find the intercept and the slope, try to minimize this guy. Okay, so that's the goal. So this is standard optimization problem. Okay, and so this, to do this requires some calculus, which we don't cover, but if you learn advanced calculus at the two variable multivariate calculus, then you will notice that it's a quadratic form. So you just take the partial derivative with respect to alpha and beta equal to 0 and solve the system, then we give you the answer. Okay, so we will tell you how to do it, but we will not have time, or we can't explain why this method is right. But if you're interested, you can check, but I'll just tell you how we derive them. Okay, but that's not different from single variable calculus, right? It's just like because how you derive the maximum, right? For a function that's maximum, you try to find the slope equal to 0, right? That's the FOC, right? The first order condition that equal to 0, right? Same for multidimensional. If this is satisfies certain kind of smoothness condition, then that will help. Anyway, so this is the formula here, right? You notice that we explained this beta is a fraction. This fraction basically is a two-part, right? If you rewrite it here, you can see we can have this is the covariance xy, okay? And this can be written as variance y, when x, y, because you can divide both sides by n, or n minus 1, depend you prefer the sample version or the population version, okay? And notice that this alpha can be given by this formula, okay? So if you rewrite this carefully, then you will see this y bar is equal to alpha hat and beta hat plus x bar. So it means that the regression line passing through the center of data, x bar, y bar. Okay, so meet the point that is the center of the data. Okay, and you can say beta is a rescaled covariance, right? It's covariance, but you divide it by variance x. Okay, is that clear? Okay, I don't see any question here, so let's go to the proof and try to give you some idea behind. As we said, the regression is trying to look at the distance and try to minimize this line, okay? The red line, the blue line, we treat it symmetrically. So regardless of where it is, it will be done in the same way. Okay, we square it, okay? So we just quickly go to the proof. Because we are not focused on calculus, then should be fine. So because expression is quadratic, and this FOC is sufficient to pin down the solution, I'm not going to explain why this is true, because this true will require study multivariate calculus. But what it says is you take the partial derivative over alpha, okay, and beta, okay, and the optimal solution, there's a minimum, right? When you evaluate this value, okay, equal to 0, okay? This is exactly same as single variable calculus, right? You would be saying, suppose you want to maximize or minimize, maybe just minimize would be easier, right? Suppose you want to minimize, right, x, right? And what you do is you differentiate this with respect to x, right? When this evaluate at the optimal point, okay, this should be 0, right? So that's the same idea here. So how you take the partial derivative here, like, right? It's just exactly same as you take the normal derivative, right? The idea is here, maybe I just open this, just take it quickly because this is fast. So this alpha minus beta xi squared, I come from 1 up to n. And now we'll try to take the derivative with respect to, say, alpha. Then the summation actually doesn't really affect you because this is the meaning of, because the operation is linear. When we add them, it's just you can take it inside. And to here, you use the chain rule. Okay, because this you have 2 of yi minus alpha minus beta xi. Okay, then you would differentiate by itself because the chain rule, so that will be give you the -1. Okay, so that is why you set this to 0. Okay, so that is what you have in, you can see from the slide. Okay, that's how you get this guy. Okay, and in the same manner, using the chain rule, you get xi because the beta your x is here. When differentiate this, you have x. Okay, so now we try to explain how you get from this expression to this expression. Okay, how do you get from here to here? Okay, let me quickly go into here because this is, we already have the here. So because 2 is multiplied, you can divide both sides by 2. The negative is not an issue here. Okay, so here is summation. You can separate one part, yi, and summation of alpha and summation xi. Okay, and this you can divide everything by 1/n. Okay, this will be y bar. This, the beta is a constant, take it out, so with beta x bar, and this is just alpha. Okay, and this y we have. Okay, so that's first thing we prove. The regression line will pass through the center of data. Okay, that's how we prove this guy. Okay, and the next part is how you, from this line, how you jump to here. Okay, but that is very simple. We just put the alpha here. That's what we have. Okay, and remember the goal is we want to solve beta, right? So beta head is just very simple. We just make beta the subject and we are done. Okay, so what we do is we will collect the things with beta on one side, without beta on the other. Okay, just make beta the subject. Okay, so there's nothing deep here. Just make beta the subject. Okay, so we just put the beta on the one side. So what you do is you put things with beta on one side, things without beta on the other side. Okay, and you put beta the subject, so that's why you have this fraction. Okay, and from this fraction, we will prove in the next slide that you can rewrite the denominator nicely into sum of squares. Okay, and same here. Okay, then we get what we want, right? Because this is a covariance over variance. Okay, so what left is to prove why this part is equal to this part, why this part equal to that part, right? How it transforms that. Okay, the proof is rather elementary, so don't worry, it's a simple proof. Okay, so the most difficult is the calculus, but the most difficult is the calculus, but anyway, we cannot do anything about that. So what we want to prove is actually this guy, same as this guy. Okay, so that is why I should prove. This is to prove the denominator, right? They're the same. How do we do that? So we will using the distributive law of multiplication, right? So A minus B times A minus B, right, will be A minus B times A minus A minus B times B. Okay, so this is, I hope that's what you know. Okay, because this is A minus B squared, right? So what we have, right, is A is here, B is here, A is here, okay? A is here, B is here, B is here, okay? So this is the part already we want to prove, right? So what it means is we need to show this is 0, okay? And because x bar is a constant, it's unrelated to I, so we can take it out. So that's why I left here. And for those who are aware, this actually is 0. Why is the case? Okay. So the summation, you can separate them, right? So you can take this xi and minus summation x bar. Okay. So you summing n x bar, so it will be n x bar and summation I. Okay. And those who know x bar meaning, right? X bar is summation of xi over n, right? So you just multiply n by the other side. So this is the same. So this is equal to 0. Okay. The 0 coming from the assumption of x bar, right? X bar is summing all the observations divided by n, right? So that n times x bar is sum of all observation, okay? Sum of all observation minus sum of all observation, that's 0, okay? So that is how you get the proof here, okay? And if you replace yi here, okay, the first one is yi, then everything remain unchanged. You should able to show that this is the same, okay? Or you can also rewrite in this form or the same idea. You can just swap x and y. And this we will be using to helpful to some of our proof later. But that is the proof for our formula, okay? Just remember, although many proof, but just remind you that what we're doing here is to prove this is the case, covariance xy and variance of x and alpha hat is coming from the idea that pass through the center, so it's y bar minus beta hat minus x bar. Okay, so this is, I hope you can have some idea about this formula, at least in your head, okay, some idea why this is true. Okay, any question at this point? If I don't see any question, then we just continue. Okay, no question, we continue. So let us talk about these 4 classical assumptions here. Okay, and so far we didn't talk about any probability, right? Here we just say, oh, find the best line to fit the data point, right? There's nothing about probability, right? So we can talk about this without going through everything here, right? But since we're here talking about probability, right, then we probably want to have some probability statement. We want to do further thing, right? Because now we have alpha and beta. We want to see, oh, is beta bigger than 0 or less than 0? Because usually the data we run is not the whole data sample, right? Suppose if we have everything collected, this is the population, that's fine, right? But we often, what we do is not population, it's the sample. And when we do sample, there's a sampling mistake, right? The sampling error. Then we want to see how beta and alpha, are they having our desired property, right? Is whether we can have estimate alpha and beta properly, right? And are they unbiased estimate, right? What is the confidence interval for those, right? And can we do test statistics, right? Can we do hypothesis testing whether different from 0 or not? Okay, so that is the goal of for having a model. Okay, so we have make 4 classical assumptions, and this assumption will give us a nice property of our estimate, okay? Estimator, alpha and beta, okay? So first, the assumption number one, so I hope you understand the goal. So we try to have a model, and under this model, hope that we have this assumption will deliver things we want, okay? So with data, we assume our model is correctly specified, which means that this is the model generated for Y, okay? So Y is actually coming from unknown parameter alpha, unknown parameter beta, okay? And this is X and Y, the data, this is a X and Y, and this is called the error, so this is the model, okay? And the second one is saying that the X are not random, okay, are non-random, okay? That means that when you talk about this will be zero. There's no random variable, okay? So that's why the variance is equal to zero. There's no variation here, okay? And that means also expected XR is just XI, okay? There's nothing, no variation, okay? And these are the parameter of the model, okay? Which we don't know it, we try to estimate, that's the goal, we try to estimate that, okay? X and Y from the data, but this variable X is not random variable, okay? This is a random variable, and that's why this is also a random variable, okay? When you say random variable, we actually means this guy is bigger than zero, same as this guy is bigger than zero, okay? Because there's some variation, right? If there's no variation, then it's constant. And we have assumption here saying that the mean zero and every error has the same variance. What does that mean? It means that for every observation, there's a random error. Okay, this random error have mean zero. And this mean zero assumption is innocuous when we have alpha, because if it's bigger than zero and smaller than zero, you can always put it in alpha. So that usually is not a big issue. So the issue is here is this one is a little bit sometimes maybe violated, need a better model. But what it means here is no matter which observation you have, it's the same variance. Okay, for those who study finance, then you would jump up and say no, right? Because it's well known that the financial data have a feature we call volatility clustering. What it means is when the market is volatile, then in the last couple of days tend to be volatile now. Okay, if the market is flat, for a moment it should be flat, right? So it's like when the market fluctuates a lot, it tend to fluctuate. When the market is flat, it tend to flat. Okay, so that means that the variance cannot be constant over time. Okay, and for those who study, I don't know, real estate or accounting, you will know also this can be problematic because when we collect data in the real world, we have sometimes we collect from geographical location, and different location can be very different, right? Suppose you look at the US map, right? And different state would have different variability. You don't expect the state in the south is the same as the north, right? Similarly, in the China, there's a lot of province. If you do auditing there, you would thinking the variance in one province can be different from others, right? So you would say every province at the same variance will be a big assumption to swallow. But of course, don't worry, this part, even this violated, we will have a different way to estimate. It's not a end of the world. It's not a big deal. Okay, this part is not a big deal. We can easily solve this problem. But for the moment, we don't try to solve it, but this can be solved. And the next one is also a little bit problematic. Is a error are not correlated with one another. Is also an issue here when you talk about financial data. And if the price have been gone up, you expect the next period, the price also go up, right? There's a observation are somewhat related, right? If you tell me, say, like the weather, right? If you tell me this moment there's a rain, then next moment I would expect rain also, right? So that would be related, right? If observation are not uncorrelated, then this assumption can be problematic, okay? So there are a lot of problematic thing in the real world, and that is you will learn how to solve this problem when you go to more advanced class, okay? So for the moment, let's take all these four assumptions as given and we solve it. And out of this, after this course, you go to other class, then you will learn. So this question asked is why alpha and beta are head and there's no head. Okay. So put it this way, alpha and beta is the usually is the parameter, the parameter, okay, which is something unknown in the population. Okay, when you say alpha head and beta head are our estimate. So this is unknown. This is usually our estimator or estimate. Usually when you write it, this is our estimator. We try to use this to estimate those. Estimator. This is a standard way you do it, and that's why I write alpha head beta head. This is estimator. This is in line with you read the textbook. This is standard way people write it. So I just try to follow those people write it. Okay. So here comes for the here comes for the important theorem that we don't prove at all. Okay. If you study advanced econometrics, then they will prove in the class for one class. But here we don't prove it. We just say it. Okay. So what we want to say is under the assumption we have here, the alpha and beta that we said, which is beta is covariance xy over the variance x, and this is just coming from this formula here. Okay, this actually turned out to be very nice thing is in the unbiased estimator. So they expected this and this is equal to this. Okay, so ask me the head is what I mean here. Head is like this one. Whole in, I hope you get it. This is head actually means this one and this one. And this is something we're trying to estimate, but what he said is what we try to estimate is this one, right? So the head notation is something like this. Is actually mu is the mean, right? So mu head is estimate of mean. Usually use x bar to do it. Okay, but anyway. And the next thing is Gauss-Markov theorem. Actually, the more important part is this is actually the best. It means the smallest variance among the class of estimate that's linear in y. Sorry, the typo in your slide, it should be y, not x. But what it means is you can see the beta, right? Just recall the beta head can be written as this, okay, yi, and okay. So this is near, let me write the y out, okay. So that means that this this is estimated beta is a function of y, okay, because this is a coefficient, right? So you just, everything is linear in y, okay? So that's why You can consider any linear in Y. Can you get it better? Then the answer is Gauss-Markov said you cannot. So in the case where when there's no computer, right, in those days, then people probably want linear, and they said linear in Y, they're actually the best. So that's a very useful theorem, very powerful theorem saying to give us, okay, we'll do the regression, not only the least square method, minimize the distance is a good idea, and if you give the model, this is unbiased estimator, and also achieve the lowest variance, which is accurate, okay? So that is what this theorem means, but we're not going to prove it, we just have it. Okay. So before we give you a break, let us give you some interpretation of the coefficient. Okay. So our estimated model, okay, is this one, right? Because once we estimate, we have alpha and beta. Just to remind you what is beta hat, okay? Someone asked in the chart, basically just the covariance x and y and variance x. And this is, as we said, is, okay, so this is what it means. And how do we interpret alpha and beta when you calculate, right? It's easy to calculate. You can, later we'll see in Excel spreadsheet that is come like mechanically. So what is the use of this tool? Okay. So remember alpha is a y-intercept, right? Y-intercept it means the value when x is 0, okay, is average of y when x is 0, okay, average value. So technically, actually, this means this. What's y given x is 0, if you care about the notation. But what does that mean here? It means that when x is 0, then what's the value of y on average? But the problem of this interpretation is not going to be universally applied, because if your data has x around 0, then this interpretation makes sense, right? But if data is way above 0, then that doesn't make a lot of sense. For example, look at the education and income data, and at least you look at Hong Kong, most of people, the data you collected would have at least 9 years of schooling, right? Or even more. So data, you don't have any data around 0. So the slope will not make any sense. Usually will be a garbage for the alpha. But a lot of time, some other time alpha may be garbage. Maybe you look at the sales, advertising and sales, right? And in that case, the sales would make sense when you have no advertising is 0, because when the data you have do not do advertising, you still have sales, right? So that then this interpretation would make sense only if you have some special thing about 0. And the second one, the more important one, is the interpretation of beta, okay? And beta is the slope, right? So it's just like slope means how x changed by 1 on average, how y changes. So do note there's on average, is an important keyword here. And do note that there's no causality, there's no causation, okay? That means that when x changed by 1, y changed by 1. But it's not saying that if we change x by 1, y changes by 1, okay? There's no causality here, okay? I just say you see this change by 1, you expect y change by 1. But it's not saying that you directly cause. Because of the fact that you just see how they related in statistics. You need more information to determine this is causality. Suppose in the lab, you change x, then you see y changes, then then you can see causality here, right? But in the real world, you observe the data, then it's not easy to see causality. Okay, you need more than regression to establish causality. And usually what we say just association, okay? Because you see the regression doesn't help you to say y cos x and x cos y, right? And also it's possible that there can be, say, right? You see can be x cos y or y cos x, right? That's because there's no hard and fast rule to say what is y, what is x, right? And also there may be a common element z that affecting both y and x, right? Suppose the common thing you call the earning equation, right? Where you have explained the income by education, right? You put the education here, right? Or schooling here, then you put income here, right? But there's hidden thing here, there's ability, okay? That will affect education and also affect income, right? So there's another thing that underlying or IQ or EQ or AQ or whatever Q, right? Affecting both, okay? So you don't know, it's just association. So we cannot say too much, but just say they're related. The best way to interpret is the variation of y is explained by variation x, okay? The reason is if you use the data y and x, you run the regression, you get the beta, but you consider other set of data, you subtract y from the mean, subtract x from the mean, you run the regression, you also get the beta, okay? So they call it demean the data set, you also get the same beta. So basically you are using the variation of x to explain variation of y, okay? I hope that is clear to you. But for the moment, let's take a 15 minutes break. In the meantime, I answer any question you might have. So now it's 5:18. So let's break until 5:33. Okay. So break until then. In the meantime, I'm just stay around to answer any question that you might have. There's a question related to exam. Do I proper notation? Of course, you write proper notation. You write the steps. So I guess that would be. I guess it's similar to all other exams and all other things you have. It's just like you write clearly. You form team of 5 is okay. I think 5 is okay. If you, yeah, 5 is okay. I think 5 would be the reasonable number. But of course, smaller is not too big. Too bigger means you would have a lot of things to say, right? Otherwise, there's no gain of doing it together, right? But so leave your question in chat. I'll answer that. So there's a question in the chat room saying why there's no change when you swap x bar y bar, because this is the meaning of the equation beta is given by variance, and the idea is the following. Look at the idea of the beta, right? Beta is covariance xy over variance of x. If you consider covariant x minus x bar, y minus y bar, and you replace by variance of x minus x bar, okay? The denominator is still x, okay? And the covariance actually is same as covariant x and y. The reason why is, remember what you do to covariant is you subtract its mean and times the other guy. So the mean of this, right? The mean of this series is 0. So basically, okay, if the data is this, take the mean, they will become a 0. And there's other question. What are the recording of the last class? I think I uploaded. No? Let me check. I think I uploaded. Yeah, my thing uploaded is already there. I can show you now. Yeah, I think in the, I switch to your view. So this one, this is the 2011H, right? You go to the YouTube, right? Go to the end, you can see this November 10, this is last class video. Yeah, this will cover last class. Y0. Oh, you just said what is Y0? Oh, maybe I give you intuitive explanation to that question. Remember what's the meaning of covariance? If you still remember, scatter plot here is the covariance is the definition is summation x minus x bar, y minus y bar, right, over n minus or n-1 depends, right? X and Y. So you have a lot of data here, right? Then what you do is you look at Y bar and X bar, right? And see each data if it's above mean or below mean, right? So suppose you everything minus the mean, Y minus X minus the mean, then you just rescale the data, same thing. The pattern doesn't change. So that's the idea why, or you can just actually prove it, same as if you look at this data, would be same as this one. With the covariance same. I hope I answer your question, but the intuitively, because you look at how when X above the mean, Y below the mean is asking always about the mean. So that's why when you subtract the same number, the same thing. Actually, not subtract this, actually subtract any number, the same thing. Same as variance. So not need subtract the mean, actually subtract everything by 1, X by 1, Y by 4, then same thing. Same as variance. If you move everything, it doesn't really change. Okay, I hope that answers your question. So here's a question, how to calculate the interval estimator when the question asks one side? Oh, that's interval estimator usually you have two-sided. I don't know how to calculate one-sided. It's one side, it's two-sided. You should go to both sides. Yeah, usually two-sided. I don't understand the question. the chart saying measuring population proportion, I guess. Mean of time, is it possible that the lower bound is negative? Well, it's okay. We just let negative is negative. We're not going to change it as we said in the class. So the proportion, if negative, negative, more than one, just leave it as it is. Or anyway, whenever you're negative is fine. I mean, just leave it as it is. Because you're assuming it's normal, then actually it's not normal, but normal means this can go to negative infinity and positive infinity, right? So it's possible, but doesn't make a lot of sense when you actually have it. So you just leave it there without going into further detail. Someone asked a question about homework 3, but I'm not sure what is asking here. You need to be more specific. Okay, I guess, oh, we still have 5 more minutes to go. Yes. Oh, someone asked me question 1C. But question 1C is not about competence level. My answer is when homework release, I will ask the TA. I guess we will be I don't know. I mean, he said he is relatively busy due to the blended class this month, but I try to push him a little bit to release quickly as soon as possible. But the answer, as I said, I will only upload the short answer. If you want explanation, you have to ask TA. You email him for if you want to know. Okay. I guess we should resume our class. The break is over. Before we continue, I would like to show you the Excel to do the calculation. Show you how we do the find the regression stuff. Okay. So very quickly, this is a spreadsheet. I hope you can see my spreadsheet. Suppose this data X and Y. Okay. And you may can you see this? I hope you can see my spreadsheet. Suppose data is like I just randomly make up some data here. Okay. And okay. So I want to show you how we calculate alpha and beta. Okay. So we want to show you how we calculate the intercept, slope first, slope, and intercept. Okay. So we want to calculate mean of X and mean of Y. Okay. That come from the using average function, average of X, right? And you can have average of Y. Okay. So let me do the formula test here. Okay. So this is average of X and average of Y. Okay. So that comes handy for the one. Okay. So the slope is just, as we said, you can just like the covariance P, okay, over the variance P of X. Okay. So that's, oh, luckily, that's a very nice answer. Okay. And of course, you can also use covariance S. Okay. Over variance of S. Okay. So either way would do. Maybe I think it's less big. Okay, so that would do the job. Okay. These two are data. Okay. And the intercept will be just y bar minus the slope times the mean of X. Okay. So that will be intercept. Okay. And since regression is so common, the recent version of the Excel actually allow you to calculate the slope directly. So you can put the slope and you put the Y and you put the X. Okay. So give you the same answer here. If you put the intercept, Y and X, then also give you the answer. Okay. So that would be, okay. So someone actually asked why if I have this minus X bar, okay, and Y minus Y bar, do we have the same result? So let me prove it. I mean, kind of verify, not prove, verify this is the case. So it's easy if you, this minus this guy, I put the absolute address. Okay. So these are all, we call demean the X, right? We take away the mean, and then we also can demean the Y. Okay. So this will be the demean the X and demean Y. So I will try to prove the slope is -4. Okay. So let's do the slope. Put the Y first and put the X. Okay, you can see it's -4. You can also try to put intercept, the same idea, but the intercept will be different. As you will see, intercept will be 0 in this case, because it is demeaned. It's not exactly 0 because of calculator is not fully there, but you can see it's as small as you can go. Because you move the, basically you move the coordinate to the center. So that's why intercept with 0, because pass through the 0 point. Okay, any question about Excel? I will come back to this later at the end of this class when we talk about the inference. But at the moment, any question before we proceed? Okay, if no, then maybe maybe I come back later. Okay, maybe I go to the slide first because it will not be meaningful if without. So now we estimate alpha and beta. So the natural question is we ask the model, right? We have alpha and beta, but also the one thing is sigma square, right? The model, we have three things, alpha, beta, and sigma square. So we will tell you how to estimate the sigma square. Why we care about that? Because by looking at this, we can do estimation and inference on alpha hat and beta. Okay, so that's something we care, right? Because we want to test hypothesis whether alpha is 0, or we often want to set beta is 0. Okay, so these are the important, especially this one is most important because we want to see if there is some linear relationship between them, right? If there's no, then it will be 0, right? So we want to check whether beta is 0 or not. Okay, so that is the goal. But now let's us estimate how to estimate the sigma. Okay. So the error term, okay, from the model is like this one. This is from the model, right? The model assumption, right? There's a constant. This is the realized from the data, right? So this is when we draw x and y, right? Related by alpha and beta, but there's a noisy term error. This noisy term can be anything not modeled. Okay, everything not modeled is captured in this error term, and this is what in the model, right? So, but what is the sample counterpart? Okay, so you use the actual data, okay, and this is coming from your estimation, right? The beta is just covariance xy over variance y, so variance x, right? And this again, I'm not going to repeat, but anyway, it's just y bar minus beta hat x bar, this alpha hat, and this one is the estimated residual. Okay, it's called residual. It's going to estimate this guy, and this guy we will use to estimate the sigmas. Okay, as we said, we want to know sigma because the model have three things we want to know is alpha, beta, and sigma. Okay, now because we have a random term, that will be another thing. Okay, so the sample variance, okay, is coming from estimate by S squared will be summing this minus 0. The mean, actually the mean, you can easily check the average of this will be 0. So that's why you can use this. And y minus 2, we don't explain it now, or we don't explain in this class because it will be same as unbiased estimator. But the easiest thing to explain why you have this is because you have X bar and Y bar, you estimate two mean already, or you estimate two parameter, alpha and beta already, so that's why you have 2 degree freedom or less. But anyway, just keep in mind n minus 2, there is something you'll be doing. And take the square root of the whole expression, that will come the standard error of the estimate. Okay, this is a technical term, standard error estimates like this guy. Okay. Now, why we care about this? Of course, we estimate sigma squared. That's done. We care. Why is it important? Because it tells us how noisy the regression is, right? If the sigma square is small, right, or S square is small, then the regression is very good, right? Because it's just not the variation is not very big, right? Basically, just it fit very well. The line fit better. The sigma will be smaller. Okay, so that would be the things why it's important. But more importantly, we want to use it for the next slide. Okay, it's the following. Okay, so the first statement is we will try to prove to you is the variance is given by this. Okay, the variance is given by somewhat complicated expression. It's like if we know the sigma square, there was sum of x square and this guy. Okay, looks all very complicated. Okay, and it turns out if we assume the error is normal, okay, and this is usually fine under central limit theorem. Okay, so that's not a big deal. And so then because of the fact that alpha and the beta are linear in y, which means they're linear in epsilon. So that's why alpha will also normal, okay? And from the Gauss-Markov theorem, he said the mean of alpha is alpha itself, okay? So because unbiased, okay? And this is given from here, okay? And we call this standard error of alpha hat. We will take square root of this guy, okay? So what is the significance of this, okay? The significance of this is, right, because then we can use t-text, right? Because you can say this, suppose we hypothesize alpha is 0, then you minus 0 over the SE of this guy, right? We have t distribution of n minus 2, which will be given soon, okay? But let us prove this guy for you, okay? Then this is, under this central limit theorem, we have this, and then we can do inference, okay? So based on this, we can do inference. Maybe so this is true. Let's see, okay? So how to prove this? Just we will have a shorthand notation. Sxx is the sum of xi minus x bar squared, and the coefficient, this is the denominator is here, right? So we can just rewrite this. This is same as minus y bar, but there's no difference, okay? So now we have variance of alpha hat, which is y bar minus beta hat minus x bar, which is definition here, okay? And first thing is y bar is 1 over n times sum of yi, so that is by default. And this y bar is, x bar is here, and beta is here, so just go down, okay? And yi, right, everything is constant, you can take yi out, right? So y is here. Then you can take 1 over n, come from here, okay? Then you have this guy, okay, come from here, okay? And variance of sum, sum of the variance, right? The variance ax plus by is a square variance x plus b square variance y. So that's why variance sum will be sum of the variance and the constant will be square. So this constant will be square, the summation is out. So just get in and all the constant will be square, okay? So what left is to show you this guy, what's this guy, okay? And what you will be doing will be a minus b squared. So it will be a squared minus 2ab plus b squared. So we will do it in the next slide, okay? So we are doing a minus b squared. So that is a squared 2ab and b squared. And variance of yi is the same as variance of epsilon I because other things are constant. So this epsilon square, sigma square. So that's why here is here. Okay. And now we have summing n items of 1 over n squared. So that's why 1 over n. Okay. And this guy, by definition, as xx. So we cancel this out. Okay. So that's left you with x bar square over sxx, which is this guy. Okay. Why the middle guy is gone? Again, this is constant, can take out. Okay. It doesn't vary with xi. And this is 0, right? Summing all the variable minus x bar is exactly 0. We have seen. So that's why we left this guy. Okay. And you can further simplify by making the common denominator. Okay. You multiply n, you multiply the other side. And sxx is this guy. Okay. And this guy you can simplify. And summing xi minus x bar square is just the same as a minus b square. Okay, will be xi square minus 2xi x bar, and this will be x bar square. Okay, and then summation of this guy is here. Okay, this guy's here. Okay, and what happened to this rest of the guy? And this is just, and this all cancel out. Why? Because this guy you multiply, sorry, color. This guy you summation, right? So this is nx prime, okay, and x bar square, and this is 2 because summing all up, so will be n square negative 2n x bar square. This, and this cancel out. So what's left here? Okay, so I go rather quick here because the time constraint and also I see it's not terribly important. I mean, also straightforward, just a little bit more complicated. Okay, but if you still you can try to do it by yourself. If you have a question, ask me. But I will want to save the time for more important thing because, as I said, next Thursday we have one class left, so we have to a little bit quicker, a little bit. So regression equation, I want to test the coefficient alpha equal to a or not equal to a. Usually a is 0. Okay, for most of our purpose is 0. Okay, so we want to test this case and turn out this is to be t because it's assumed normality, and then we replace by the sample version that everything will works out. Okay, same as we have seen. Okay, it's a t, and then it will not be surprising to you that how we can do the point estimate, right? This is the point estimate. right? Because this is beta hat. Okay, so the standard way to do it. And do note that here is marginal error. There's a typo in this slide. It's not the interval width, it's the marginal error. It's 2n over n minus 2 alpha over 2. And this is the what we have seen just now. So this is the interval estimate. Okay. And don't worry, all these things later you will see will appear in the Excel output. Okay. Usually it's directly given to you. So you just need to know what's the meaning of those. Any question? We don't need to rush because I think we have time. We have enough time. Any question you want to ask at this stage? Okay. If no, then we go to the next one. Okay. So this one is the most important. I think it's the most important thing. Okay, is to look at how the slope coefficient looks like. Okay, this will prove. The proof will be much easier. So don't worry. You can see expression is much easier. So this is not complicated. Okay, so turn out to be the variation of the beta. It's just same as this guy, but you would depend on how x varies. Okay, if x have a big variance, then the variance of beta will be bigger. Okay, so that is what it means. Okay, and if everything is follow normal, and this beta head, which is coming from the covariance x and overvariance, will have a normal distribution again. Okay, and it is unbiasedness, right, given from the Markov theorem. This is real proof. Okay, and we call this standard error of beta would be like this one. Just replace this by this guy. Okay, remember S is just summing all the error. Okay, over n minus 2, take a square root, right? So just make sure remember this. So now what we want to do is to prove this exactly the beta head guy. Okay, let's prove it. So this Sx6 is sum of all the x, right? And this is the definition. So we do not need to, it's given from there. So we just directly calculate what is this guy, okay? This guy just plug in, is the variance of this guy, okay? So remember x is a constant, so you can take it out. So the whole thing can take out, you take square, right? The idea is variance of a of x is a squared variance x. So that is, you take this out, okay? Of course, first you take the summation out first. So basically, it should be summation I 1 up to n, and you do the variance of this first. Okay, and then this will be taken out square, so that's why square here, square here. Okay, and variance of this is sigma. Okay, and the next step will be, this is exactly Sx6, so it cancel out. So that's what you left here. It's very clean. It's sigma squared over Sx6. Is that a question? Because most of you don't care about the proof, so let's continue. I guess you don't care too much about the proof. So what is here is I want to do a t-test on the slope coefficient. Okay, I want to see B beta is equal to value B, usually is 0, right? Because if B is 0, beta is 0, that means that there's no relationship between X and Y, right? So you cannot say anything, Y explained by X, okay? So this is the key step here. In the Excel is always -0, okay, you will see. Excel output, okay? So one more slide, I will go to Excel. So you can see the common interval, okay? You just point estimate, because I'm biased, you just give what it is, right? The margin of error is like this, so this is the common interval, okay? So maybe I should go to the, if no question, I go to the Excel. That would be the most fruitful, okay? So the good thing here is there's a Excel add in the data analytics. So data analysis have easy calculation for regression. So please go to Excel, go to data and data analysis. Okay. So see it when you click this one. Can you see my Excel? I guess you do. So then you go to the, at the end, you will see the 1, 2, 3, last to the 6. We'll have the regression. Okay. Okay for regression. Okay. And then you put the input here one by one. Okay. So you go to click on Y range. You can click this as a B to, here is B, as a B1 to B7 for my case. Okay, depending on data. And you can input X range, just highlight the X range. Okay. So you have X and Y. And because I've labeled at the top, so I put label here. Okay. And now let's see where I want to output this. I want to put it here, maybe. Okay, you want to put whatever you like. You put OK. Okay. So let's see the result. Okay. So we have this multiple R square, R adjust. We don't talk about that. We'll talk about R square next class. Okay. But this we are not going to, we are not going to explain. We don't explain those. Okay. So standard error of regression, we have cover, right? Remember how to, error is a square root of the residual, sum of square residual. Okay, this is just to remind you, this part is coming from sum of this square and -2, right? How to calculate this is just you get the data minus alpha hat minus beta hat xi. Okay, so this is the formula, right? I think with your Excel skill, you're able to calculate by yourself to prove this is what it is. Observation 6 is just number of observation. Okay, and here we have sum of ANOVA. This is the same idea here because you are trying to explain things, but we'll talk about this next class. So this is also very important, but this part will be, we'll explain in the next class. So just keep in mind, we'll have the same ANOVA in the next class. So what I want to say is the very last thing, or also the most important thing here. Okay, so which is this one. Okay, so you can easily see the coefficient -0.4 and 23.55 is exactly what we find here. Sorry, it's this number and this number, right? So these are the slope and intercept, right? It's exactly the coefficient, intercept, and slope. Okay. And the standard error is just what we said is the standard error of the intercept and coefficient, right? Just to remind you that this guy, right, is just from the formula, right? It's just S over SXX. Remember correctly? Yes. Maybe take a square root. Okay, so that is the estimate, and this is much more complicated, but it already given to you, so you don't need to worry in your mind. Okay, so that will be some error. So what is the t stat here? Okay, t stat here is coming from the idea where, say, intercept is in the alpha equal to 0, it is testing this hypothesis. Okay, so that's why the t stat is coming from, if you take this, divide this, you should get this number. Okay, similarly, if you divide this, should give you this number, right? Because this coefficient is alpha hat, right? Alpha hat minus 0 over SC of alpha hat is our t distribution, right? Should be following t n minus 2, right? And similarly, this is alpha hat, this is beta hat, right? This is beta hat, okay? And this is SC of beta hat, okay? And this t stat is beta hat minus 0 over SE beta hat. Is that clear? What the number is? Okay. The next thing is you will see the p-value here. Okay. These two p-values shows that they are not smaller than 5%, right? So you reject the case where alpha and beta are 0. Okay. So that means that effectively, first x and y are really not very related at all. Okay. And also the intercept is also no different from 0. Okay. And the next part is you try to look at the confidence interval estimate. Okay. You will see the interval estimate is rather large, right? It's negative 11 to 58, right? So that's include 0. So that's why you cannot reject it different from 0. Same for the slope, right? It's also very large, is not different from 0. Okay, so you can see this is already very simple calculation. Just click, then you get all the result, and we describe all the result already in the slides. Of course, we didn't talk about the ANOVA. That we will cover it in the next class. Okay, but before we end today, I want to remind you that if you run the regression, which I encourage you to do for your project, is you should draw a scatter plot first. So you should have a data and have a scatter plot, okay? And you will see, of course, we have fair viewpoint, right? You can easily see that you may want to, for this graph, right? Maybe you want to fit a line in this way, seems a good fit, right? But same can said about this line is also a good fit, right? And this can also be, this also may be a good fit, right? So that's why you will see the intercept and the slope is all cannot say anything, right? Can be very positive, can be very negative, can be include 0, right? So that's why you have the conclusion that you cannot say too much because the variation is too large to say anything. Okay. So we will finish the rest of all the slides and also the course material next class. And we don't have class on Thursday next week because of the graduation. So that's why the school have no class on Thursday for all other classes as well. So I will see you next Thursday. Have a nice day. Thank you. Bye-bye. I mean, I stay around to answer the question you might have. So some question, why sigma square whole in? Can you tell me which slide you mentioned and refer to? I guess you are talking about why this become S? Or take the square root. Hello?
But the statement, but the above is for the population and the below is for the sample size.
Sorry, I didn't, which, is it talk about this slide?
Yes.
So it's just replacing, actually this is exactly what you do in the old days. So suppose you said, okay, X bar, right, is normal, mu, and sigma square, right? In that case, actually small n, right? So usually you would do is this minus mu and over sigma over root n. You take a square root of that.
Yes.
It will be normal, right?
Mm.
But this with a t, can you see?
Yes.
You replace sigma by s, then become t. That is what we are doing here.
Oh, I see. I got it. Thank you.
So any more question? I'm happy to answer it.